Hi everyone, Professor Christina Sover here from Cal State Long Beach speaking, and in this video we're going to discuss an example involving toothpicks to create a pattern and use our intuition, and I'll also show you some more concrete ways of solving using an arithmetic sequence as well. I personally prefer to use my intuition because it really is impactful in how I'm visualizing these different patterns. Most often, these patterns are made with toothpicks or matchsticks or legs or pieces, however you want to think of these little sticks we have in the picture. That's typically what they're made with. In this example, it's in your book in chapter 13. It's activity 11. And you're trying to make a function rule or a pattern rule based on the values provided. We want to figure out, looking at this making row of squares of toothpicks, um, how many toothpicks you'd need to make 100 of these such squares. Example, this is one square, these are two squares, and so on. So you want a row of 100 of those. More generally, how many toothpicks would it take to make a row with n squares? When most people see questions like this, they start about thinking about a table. And so they think of number of squares, perhaps, as the input, and then number of toothpicks as the output. And that's totally valid. Let's do that together first. So when you have one square, you have 1, 2, 3, 4 toothpicks. When you have two squares, you have 1, 2, 3, 4, 5, 6, 7 toothpicks. When you have three squares, well, you have those 7 from before that I see, and then 8, 9, 10. 10 toothpicks for three squares. I'm noticing already, to go from 4 to 7, I add 3. From 7 to 10, I add 3. Let's count how many toothpicks I need for 4 squares and see if I can't get to some pattern. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, that one's way more clear. 10 to 13, and just add 3. That's easy for me to see. So I'm conjecturing, to make this pattern, I have to add 3 to get to the next number. So if I wanted to get to 5, I would just add 3 and get 16. Since that's happened for the rest, I'm just going to assume it keeps working that way. But I want to get to 100. Do I want to keep adding 3 all those times to get to 100? It's not going to just be jump, add 3, get 19. No, it's something adding 3. And then for n, how do I get there? Oh no. So making this table starting like this is totally valid. It's wonderful. I want to look at it another way as well. I'm getting kind of stuck here. So I'm going to erase all these little tick marks that I put on the squares and on the little toothpicks. And think about the inside toothpicks and the outside toothpicks. So I'm going to add on to this chart I have here, just extend these lines. So we have number of inside toothpicks, and then the number of outside toothpicks. Because that's how I see it. I see these interior vertical toothpicks going on. It's my inside toothpicks. And then I see outside toothpicks. These sticks that make like the box on the outside of all the squares. That's how I'm visualizing it. I'm going to highlight all of those in pink. All right, so I'm going to start with inside toothpicks, color coordinating as I go. In the first square box, I didn't highlight any orange, so there's 0 inside toothpicks. For 2 squares, there's 1 inside toothpick. For 3 squares, I highlighted 2 parts, so there's 2 inside toothpicks. For 4, there's 3. Ooh, what do I notice? The number of inside toothpicks is 1 less than the number of squares. The number of inside toothpicks is 1 less than number of squares. 1 is less than 2 by 1, 2, 3, 3 to 4. So I think for my number of squares being 5, I should have 4 toothpicks. So if my number of inside toothpicks for 100, I'm thinking it's going to be 99. Ooh, and I can already get somewhere. I can fill in that last box. For n toothpick squares, I should get, for orange inside toothpicks, 1 less than n. 1 less than n is n minus 1. Ooh, I'll write that down because that translation sounds really important. Let's write that down in a different color. 1 less than n is equal to n minus 1. That seems pretty important to remember, just how translations work. And that helps me understand, like, when I'm using variables, that n minus 1 is a number. It's the number that comes just before n as a whole number. Um, n minus 1 is just the number 1 less than n. I know that sounds silly and I'm repeating myself. I apologize. Let's erase it so we know that before I didn't know what goes in there. Now I'm not done yet. I still have my outside toothpicks. And for me, this pink isn't really showing up very different. So I'm going to change it to, let's try this brown color. Oh, that's much clearer for me now. All right, so in one square, I have 1, 2, 3, 4 toothpicks. So let's write that down. And in 2 squares, I have 1, 2, 3, 4, 5, 6 toothpicks. And in 3 squares, I have 1, 2, 3, 4, 5, 6, 7, 8 toothpicks. Ooh, 4, 6, 8. Oh, that 8 went to become a circle. Sorry about that. I bet you that for 4, it's probably going to be 10, but I want to count it to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Haha, my intuition was correct. When I'm counting the outside toothpicks for each number of squares increasing by 1, I'm just adding 2 more. 12. Oh, look even further. 4 to 1. 6 goes to 2. 8 goes to 3. 10 goes to 4. 12 goes to 5. Well, I keep counting by 2's here to get there, but I'm noticing, at least with the 5 and 12 situation, it's almost as if I'm doing 5 times 2 plus 2 more. Let's see if that works for the 10 and 4 situation. 5 times 2 plus 2 more. Yeah, about 4 times 2 is 8. 8 plus 2 is 10. Okay, cool. Let's check for the rest so we can conjecture to see if it's going to work. So is 3 times 2 plus 2 going to give me 8? Yes, it is. Is 2 times 2 plus 2 going to give me 6? You betcha. Is 1 times 2 plus 2 going to get me 4? Always. So I'm going to do 100 times 2 plus 2 to get the number that's supposed to be there, which is 202. Oh, but wait. How do I get n? All right, let's take a look. I just plugged in the number that came from above. Let's double check that. To go here to here. Yeah, it was 100 was the number above. So to get the number down here, I'm going to do the number above, n, times 2 plus 2. And the 2's and the times 2's are always the same, so nothing like that's going to be different. So my formula for the number of outside toothpicks for n is 2n plus 2, or 2 times n plus 2. So the number of outside toothpicks, that number is just 2n plus 2. Cool. So I know for the total number of toothpicks, I should get, let's actually write that down. The total number of toothpicks for n squares is equal to n minus 1 plus 2n plus 2. We could combine it, but n minus 1 is my inside toothpicks, and n minus, or n, excuse me, let me start again. N minus 1 is my inside toothpicks, and 2n plus 2 is my outside toothpicks. Oh, I'm silly, I even had a box up here for it. N minus 1 plus 2n plus 2. And with this information here, I was able to fill in that spot. I could do the same thing for 100 if I wanted to. Let's see, 99 plus 202, well, that's 301. I think so, right? Yeah, cool. So though my intuition might have first gone to look at the number of squares, count the number of toothpicks, I wasn't able to complete my intuition. But once I said, okay, what do I see in this picture? I personally saw inside toothpicks and outside toothpicks. You might have seen horizontal toothpicks and vertical toothpicks. You could have made a list that way. Or maybe you saw some overlapping borrowing situation. That's also totally valid. Regardless, the way I counted it, I had n minus 1 plus 2n plus 2. And that's really impactful. The model that I came up with, the n minus 1 plus 2n plus 2 is my model, directly relates to the number of inside toothpicks, the number of outside toothpicks. Now, for lack of space, I'm going to need to erase things, and I want to show you the arithmetic sequence. So let's erase this beautiful work we did. That's totally fine. I'm going to leave what I have in black in the corner for the boxes, for what I know the answer is supposed to be there. And I'm going to go farther and talk about an arithmetic sequence. Arithmetic sequence. There's a formula, and that formula is a plus d times n minus 1. Now, a is the initial amount that you start with. Initial amount that you start with. D is the common difference. And the n minus 1 just kind of stays there. So the initial amount that we started with was, or we started with, what are we talking about here? Do we care about the number of squares or the number of toothpicks? We're trying to figure out how many toothpicks. So the initial amount would come from the toothpick column of 4. Okay, so I should put a 4 plus common difference. So we noticed this earlier already on our own. Our common difference is how much we jump from space to space, and we saw you add 3. So we should add 3. And then the n minus 1 just comes for fun. So based on the arithmetic sequence, our formula is 4 plus 3 times n minus 1. But where does the 4 come from in the context of the picture? It's just the number of toothpicks to make one square. This is less meaningful than how we had over here in black, that n minus 1 came from the interior toothpicks, and the 2n plus 2 comes from the exterior toothpick. So that's one drawback of just using the sequence formula. Um, and then the 3 in front of the n minus 1 in the arithmetic sequence, that one's a little bit more impactful. It's the amount that I have to add to get to the next figure in the sequence. But the whole formula doesn't have as much rich context as the one that we used our intuition to find. Another question people might have is, well, how do I know that these are both valid? I'm just going to simplify. That's the only reason why I would simplify in this case, is just to see what I get. So distributing, we get 4 plus 3 times n minus 3, and then we get 3n plus 1. So I should get 3n plus 1 when I simplify my intuitive formula as well. Well, n plus 2n is 3n, minus 1 plus 2 is plus 1. So they match. Cool. So these are both directly related. And so that's how you use intuition in one way, and that's how you use the arithmetic sequence. I personally, again, believe that intuition is more impactful and gives for more rich understanding of the content. Connected to this material is a paragraph explanation of what went wrong or what went on in this picture, how it goes throughout, and there's a discussion that's related to these diagrams. We have several students who talk about the different ways of visualizing this diagram. We look at Mike. He says, I needed 4 toothpicks for the first square and 3 more for each of the 99 squares after that. I got 301. In general, Mike's argument suggests the rule 4 plus the quantity n minus 1 times 3. Now, Mike did a way better job explaining his picture than I did with the same formula before. Um, and I like that a lot better, that it's 3 more for each additional square after that. Uh, when you relate it to the whole squares throughout, it actually sounds a little bit better. Totally valid quality explanation. Nadia says, I checked 2 more cases and they worked, so it has to be all right. Just checking 2 more cases is not enough. With more practice, you'll find that maybe something works for the first couple of examples and not for the rest, or vice versa. It works just for the end case somehow, but it doesn't work for the beginning case. So there's an error somewhere in there. We look at Oscar. Well, I put down 1 toothpick, and then every time I put down 3 more. I got another square, so 1 plus 100 times 3. In general, Oscar's reasoning suggests the rules 1 plus 3n. Whew, I'm going to have to color that one. I'm not sure what's going on here. So I put down 1 toothpick. 1 toothpick. Let's just say it's the leftmost one. Okay, that's consistent throughout. Then every time I put down 3 more. 1, 2, 3. 1, 2, 3. Oh, that works out kind of cool. He makes like backward C shapes each time. I like Oscar's explanation. When you can make the consistent growth pattern happen, it's a great formula. I love it. Now, Paloma says, across the top, there would be 100 toothpicks. Let's go across the top. And in the middle, 101. And on the bottom, 100. So 301. In general, Paloma's reasoning suggests n So that's across the top. Oh, 1 there, 2 there, 3 there, 4 there. That matches the number of squares, so n makes sense for that part. Then an n plus 1 in the middle, 101, so it should be 1 more than the number of squares. 1, 2 there, that works. 1, 2, 3 there. Yep, that's good. 1, 2, 3, 4 for 3 squares, and 1, 2, 3, 4, 5 for 4 squares. Since that same growth happens every single time and it's consistent, and I can color it the same way, valid explanation. Let's just check that last bit there. And then the bottom is another 100. You get an N. Yep, 1 for 1 square, 2 for 2 squares, 3 for 3 squares, 4 for 4 squares. Again, because the same coloring pattern works for all of the different figures for every way, it's a valid explanation. I love it. Kwan says 100 squares would make 400 toothpicks by themselves, but when you put them together, you don't need the extra ones inside, so subtract 99. In general, Kwan's reasoning suggests the rules for n minus the quantity n minus 1. All right, let's take a look. His explanation doesn't make sense for the first picture when you're thinking of 100 at once. But what I'm hearing from Kwan is that 1 square needs 4 toothpicks. Yes, that's valid. So every square needs 4 toothpicks if you were thinking of them individually. If you were trying to make square boxes, let's say. Ah, but then he talks about when you put them together, you don't need the extra ones. The extra ones come right here where we have overlaps going on, where I'm circling orange. In the first square picture, I didn't circle any. In the second square picture, I circled 1. In the third, I circled 2 overlap extra spots. In the fourth, I circled 3. We saw this before. N minus 1 makes sense here for those extra ones. Kwan's reasoning is lovely. Now, Ricky says, everyone asked the same thing. 103. So he just asked, not valid. You really want to use your own intuition before you go talking to somebody else, or your own work or your own idea before you go collaborating with other people to provide more insights and to be able to be on the same conversation. And just saying I asked other people and they got it is not enough. I believe that's all we have for this video. Again, we were talking about trying to make patterns and recognizing different rules. We've used intuition, talking about inside toothpicks and outside toothpicks to get the n minus 1 plus 2n plus 2. You can use arithmetic sequence, or as the student showed, there's many more ways of thinking about these different intuitive ideas. If you have any questions, don't be afraid to ask. I'm just an email away or a Teams chat away. Thank you so much for watching. Can't wait to see you in class. Talk to you soon. Stay safe.